Welcome back to another episode of the Machine Learning Basics using ML.NET. Last time we trained a naive Bayes model, a predictor that would predict whether some email content, if I'm not mistaken, textual data, is either spam or ham. We explored some some techniques used more in the NLP space, natural language processing space. So today I don't want to use textual data, but rather I want to show you how it's done training a classifier on image data, which means like a picture. Image classification is a common practice in the computer vision space. Quick reminder, if you want to access the materials used in these videos, you can become a member on kisco.com/members. Scroll down to become a member, after which you should be able to download the source code. Or if you prefer Patreon, go to patreon.com/kisstupid to get access to those materials. By materials, I mean these notebooks that I've created using Visual Studio Code. And there's a bunch of theory. And then there is always an exercise. Of course, I also like to use other blog posts because they always have nice visuals to help understand these more complex concepts. So let's briefly go over what a decision tree is. And it's kind of easy to visualize. It's basically some kind of flow chart. For example, is the weather sunny? Okay, let's check the humidity. Is it high? Is it normal? No, yes, whether I should go play golf. If it's cloudy, I'm always going to go play golf. That's just because this table, every time the weather is cloudy, there is a yes. It's a high probability that I can play golf just because of the data that we have now, the sample data. When the weather is rainy, I would imagine it's unlikely to go play golf. Let's see if there's strong wind. We don't want to go. If there's weak wind, we might want to go play golf. So you could almost, if you're a programmer, which I assume you are, a coder, then you can kind of see this as a conditional, as a bunch of conditionals, if else, if else, if else. Let's visualize it a little bit. This is like more like, I think from one of the previous videos where we would try to find the best fitting separating line or decision boundary. And with decision trees, it's a little different. Let's say these are apples, red apples and green apples. The first decision boundary can be, well, the color feature, so red or green. And then we'll draw a rather binary decision boundary between that. So red or green. And then maybe another decision boundary, maybe more like the level of acidity or something like that. Maybe that looks more like this. And then another question or feature. We can keep going and keep drawing these kind of boundaries until we get like an answer, red or green or yes or no. So we basically keep splitting the tree based on a single feature or condition, like the question. And we continue, yes or no, binary decision before we go to the next feature or condition, until there are no more. So that's kind of, let's see. So you start at the root node, you keep splitting decision node, and terminal node is actually called a leaf. Is, this can be yes or no. Another decision, yes, no, and so on. Root node, leaf node, subtrees, pruning. If you want to learn more, definitely I'll leave the links into the notebook as well to get through this. Then there's a few more concepts. Each split is chosen to maximize information gain or minimize impurity at the current node. There are, for each of those methods, there are some mathematical formulas calculating either the maximum information gain or either the minimum impurity. First, go over this. Of course, the decision tree is easy to visualize and interpret, since we can make these flowcharts, which are used by non-coders as well. This is interesting, handles both numerical or categorical data. So like we saw, the weather can be sunny, rainy, or cloudy, but we could have also worked with temperature being a certain continuous value, like 30 degrees Celsius. Automated feature selection is automatically identifies the most important features for decision making. This is pretty interesting, and if I'm not mistaken, the most important feature will also be at the top. In our simple example, that was weather, because that seems to have the most weight in the decision making. Handles nonlinear relationships, maybe like we simply saw in this little drawing. It's not just one linear function to separate the data, but we can keep going to capture more complex splits. Overfitting, if you forgot what that is, it's basically it is too well attuned or too well trained on the training data, and it performs very well on the training data, kind of almost memorized it. It's not fit for generalizing, so it can't really handle new data. It's going to perform poorly on data it hasn't seen or hasn't trained on. So, to get a better understanding, I asked my LLM, let's see, entropy measures the amount of uncertainty or randomness in a set of data. In the context of a classification problem, it represents the impurity or disorder in the target variable, the class labels. So, playing golf, yes or no, or the higher the entropy, the more random and unpredictable the data is. In information gain, this measures the reduction in entropy when a feature is used to split the data. The goal is to make splits in the dataset that reduce the amount of, the level of impurity or disorder on both ends of the split, since it's often a binary split. So let's ignore these ones. I've probably drawn this line, or maybe like something like this. Or worse. And I guess training the decision tree is to find the best, like we train any classification model so far, is to find that best fitting, the best decision boundary or the best separating line. So I assume that for a decision tree, we're also trying to find the best separation to reduce the uncertainty, or the, let's see, what words do they use? To reduce the impurity or disorder. So I assume, let's say we do this, now we have more disorder on both sides. We have this class and we have this class, but we only have this class here. A lot of the same class, so I assume that's going to be more disorderly. This is also going to be more disorderly than this split, and so on. So the least, or the most pure, or least impure, or the most orderly might be this split to separate the red apples from the yellow or green apples. And then when we, for example, see that this one has a higher entropy than, for example, this line, then we might move even more to here. Let's say we have this line as well. We tried that. We moved a little bit above, and it keeps getting better and better. The closer it gets to the center. And then this is This still has some impurity, I assume. But yeah, the information gain is basically the, let's say we moved, this has a very high impurity, this has a little bit less impurity, sorry, let's keep it at entropy. This has a very high entropy, this has a smaller entropy. Then the difference is basically the information gain, trying to achieve as low as possible entropy. We try to increase the information gain even more. That was, yeah, not the clearest explanation. I'm also kind of refreshing this information, although they say it's the easiest to understand. Yeah, it's a little bit vague for me. Feel free to go into the comment section and after you have a better understanding than I do about this, and explain it to me. This is, of course, this entropy and information gain is during the training process to find these conditions or features on which to split, or feature values even, on which yeah, to make a decision node and so on. If the impurity is, or the purity is 100%, then it becomes a leaf, like a yes or no, basically the outcome. Okay, let's see. This to find the best decision boundaries, so during the training process. Instead of using entropy and information gain, there is, like I mentioned already, you can also measure the impurity, which is, as I understood it, a different calculation, mathematical equation. But well, the concept is similar. You want to get a lower impurity. So it's called Gini impurity, which is just an alternative method to the entropy method. Then there are some applications of decision trees, but these seem to be, well, just general classification applications. Anyhow, we are not out of the woods yet. The reason I touched decision trees is because it's, well, it's an important concept in, or algorithm in, the machine learning space. But there's something else you can do. Instead of having just one tree, you can create an entire random forest, which is basically multiple decision trees being trained and then used for classification. This time we are going to, well, the outcome of that, so each tree is going to get its own outcome. Could be the first 5 trees could have an output of yes, and then the 6th one no, and then the rest could be also yes, outputting yes. And then we will have to make a decision, so which is basically majority voting. If the majority votes yes and just the minority votes no, then we're just going to predict yes as the final prediction. Let's see, advantages of majority voting. By combining multiple predictions, majority voting can lead to improved overall performance compared to a single model. Okay, robustness should be less susceptible to overfitting and noise than an individual model. Then you have types of voting techniques. But the whole reason why we cover this majority voting is now you basically have the concept of combining classification models, which is pretty interesting. It doesn't have to be decision trees per se. It can be a combination of, like, maybe a support vector machine with a naive Bayes, with a decision tree, and maybe logistic classification model in the mix. It could be a combination of different types of classifiers. Random forest is typically going to use multiple decision trees, not necessarily other types of classification models. But we can then speak of as ensemble methods, which is basically, it's almost like a random forest, but instead of just decision trees, it can contain multiple types of classification models. And I do think this is pretty interesting because, of course, it's likely better to have multiple classifiers solve for certain, be run on a certain data set, and then either you pick the best classifier or you combine the classifiers to get a better result. It's definitely an interesting concept. So you see multiple decision trees, and then the outputs of these are going to be summarized, let's say, and the majority output wins. So either yes or no. Wait, this is class A, class A, class B, so 2 class A's, so it's class A. And this is called bagging. Talking about bagging, bagging creates multiple instances of a single model and trains them on different subsets of data. Okay. Have we seen that already? Some kind of cross-validation or something? Boosting is, which is light GBM, is a gradient boosting, and the M is machine. You've got XG boost and you've got ADA boost and maybe other kinds of boosting models. Iteratively trains multiple weak models like decision trees or other types, with each subsequent model focusing on the errors made by its predecessor. So boosting is training multiple models in sequentially. Stacking trains multiple models independently and then combines their predictions using another model. And then at the end we put another classification model that combines the predictions of previous models into a final decision. GBMs use an iterative process to train decision trees, with each subsequent tree focused on reducing the error made by its predecessor. This process continues until a stopping criterion is met, e.g. maximum number of iterations or a specified error threshold, and so on. Why I generated this response is to see the difference between bagging, boosting, and stacking. And then because light GBM is a model trained or a technique, a algorithm that Microsoft came up with, which it's said to be more quicker or more effective or efficient, at least, than the XG boost or the ADA boost, if I'm not mistaken. So, and that's also the only one that I could find to do the exercise with, because if you're still with me, you didn't fall asleep, I want to do this multi-class classification on image data. In this case, the images are a number between 0 and 9, including 0 and 9, which are handwritten digits. And the point would be to predict, if we give another handwritten digit as input data, to predict what the digit should represent, what the input should represent, which class. So the classes would be 0 to 9, including 0 and 9. Let's see. Then by using this source, how to choose an ML.NET algorithm at LightGBM multiclass trainer is a thing we can use. And there's not too many multi-class classification trainers available. Naive Bayes. Maximum entropy multi-class trainer. It's also one we could have used, but we're not in the linear algorithms anymore. We are in the decision tree algorithms for this video, so I used the light GBM. Okay, because fast tree is what I was initially gonna go for, which is more like a decision tree, if I'm not mistaken, but I only find the regression trainers or the binary classification for fast forest as well. So the random forest, it's also binary or regression. Let's take a look at the data set then, which are those pictures or images with handwritten digits between 0 and 9. What typically happens in an image classification task or exercise is we take the resolution of the image. So this is going to be like a 30 by 30, I'm just guessing. And for each, well, the width and the height, so 30 by 30, but for each pixel, we are going to get the pixel color value. So that is going to range between 0 and 255, of which 0 is a black pixel and 255 is a white pixel, so on a grayscale. And we're going to have a model, classification model, train on that and find the pattern for it to learn what a picture of 0, for example, can have a lot of black pixels in the center. A picture of 1 can, for example, have a lot of black pixels on the sides and just a few in the center, and so on. So that's typically how it goes. Now this is already scaled in some way. We only get 64 columns, which is an 8 by 8 picture. But these values range between 0 and 16 instead of between 0 and 255, because they applied some kind of normalization technique on these images. The output of the images, it's not really an image, but it's gonna be it looks more like a float array of 64 values between 0 and 16. That's also going to be the data set. We've got a validation set, which we'll use for the test as test data. And then we have a train set, which, so we have a row count of 1,797, just all values. And here the train set is about 3,823. So the test set has like half the amount, more or less, than the training set. Okay. So we're going to start simply by visualizing the data again, so we get the right packages installed, data analysis and Microsoft ML.NET. Don't forget to use them. Also Scotplot to visualize, plottables, formatting for the charts. Input data this time is going to be a vector type, so that float array 64 values. The number is going to be column name pixel values. Number is just going to be a float, the label actually, 0 to 9. And that's the last column. It's a bit confusing. This is the last column. This is the size, if I'm not mistaken. Output data is simply going to be a float of score. That's going to be, because we're doing multi-class classification, it's going to give us a probability score for each class. We've got some sample MNIST data, which I copied from the multi-class classification sample. The links are at the top. Multi-class classification MNIST, which the first one should be number 1, values for number 1, the second one for number 7, and the third one for number 9. We've got 64 columns in one sample. Loading the trained test data, initialize our ML context. Like the example, we load the training data. And so the features are the pixel values and the label is the number column. The first 63 columns. The test data, similarly, we don't have a header and our separator is comma. Row count 3,823 for the train data. We use that to visualize our data in a data frame. So what do we have now? Let's see, just the first 3 rows. This is a number 6. This is also a number 6 and a number 7. The values for that, the first 3 rows of the train data. Then we construct so to visualize, we make bars per class and the amount of records for each class. Visualizing the data balance or imbalance. basically doing the construct bar per class. And then we see the classes 0 to 9, and then the amount of samples per class, which seems to be pretty well balanced. And then we order them again just to see 0 to 9. We have a very well balanced data set. Maybe we don't have enough samples per, because our model is again a bit garbage. Our data processing pipeline, we map so the label is our number column, and we concatenate the features. We kind of make a vector of these pixel values, concatenate all of these to become a vector. Okay, then we install the trainer that we want to use. It's going to be LightGBM, because that's a multi-class trainer, not just a decision tree, because that can only do the binary classification. So LightGBM, label column, feature column. Okay. Number of leaves. Let's see. Maximum number of leaves in one tree. So these leaves were the output nodes almost. Maximum number of iterations. A new tree is created in each iteration. So this is the number of trees that are going to be created. Minimum example count per leaf. Minimal number of data points required to form a new tree leaf from tree samples. Feel free to play around with that. I did, but I didn't get any better results. We fit the model, prepare our methods for printing the metrics. And if we do so on the test data, check the predictions, then unfortunately we get a bad performing model. So value between 0 and 1, close to 1 the better. Yeah, okay, we've got a 0.2, that's not good. 0.2 again. Log loss, closer to 0 the better, so this is way too high. And then a log loss per class, so the log loss is that error rate. Log loss per class, closer to 0 the better. This is good, this is bad, 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 decent, bad, 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 all kind of terrible. Consuming the model, passing the input data type and the output data type. Print prediction is, instead of the metrics, we kind of want to have the probabilities this time per class, so 0 to 9. We're gonna print the predicted value, which is basically the highest probability. We'll see that in a bit. And then we would like to have the index of that highest probability to know which class. So this index is this, 0 to 9. We want to know which class it actually predicted. So this should be the score with the highest probability, or the class with the highest probability. And then the actual, we're just passing it. We know that from the sample. If we then go down and we try the first sample, which should have been a 1, is predicted as a 7 with a probability of almost, well, of 99.9%, 98%, but it's completely wrong. How did that happen? That's a good question. I messed up again, or the example is wrong, but I doubt that. Or we just have a very, not enough samples, or very, we didn't specify the model well, like all these, but I did change these things a lot. Didn't change the output that much. Okay, then the next one. So it's also important to know, is because now this is a multi-class classification. You're never going to get a 1 at these things, because well, unless it gives also a 0 for 9 and then a 1 for 7, then basically the sum of these probabilities should be 1. And then the highest probability is likely what the correctly predicted value, although when assuming we have a decently performing model. So it's very convinced that it's a 7. Could maybe figure out why that is by looking at the images of 7, and maybe we'll see it's just, yeah, it just looks too much like a 1. Or the dataset doesn't have enough variation. We got all 7s looking like 1s in the dataset. It's all possible, so data quality is definitely a possibility. The second one should be a 7, but it predicts a 1, so it's the opposite. So maybe I messed up, but okay. So it's pretty high certainty for 1, and a little bit for a 6. Then the last one should be a 9, but it predicts like a 5, sometimes a 4, depending on how I specified the parameters. Let's see, so 5 is the highest one. No, 4 is pretty low probability. 7 is low, 8 is getting there. Well, and 9 is very low, which it should be. So that's a bit of a problem here. It's really giving me like a 0 for 7. Well, it should be a 7. And here it's giving me a 0 for 1. Well, it should be a 1. So that's a bit concerning. But yeah. We will not linger too long on these examples, and because I really want to get this over with and get to the more exciting stuff. But that's going to be for next videos. So if you want access to these sources, don't forget to check out qiskcode.com/members, become a member, or go to my Patreon if that's your preference. Also check out the products on qiskcode.com or get my NuGet packages for free.